Hello everybody. In this lesson I'd like to look at how we rationalize denominators, and in particular denominators that have square roots in them. So suppose you find the answer to a problem you're working on to be 4 divided by the square root of 2. But the answer is supposed to be 2 times the square root of 2. So you might wonder if perhaps you got that wrong. And yet when you plug these into your calculator, 4 divided by the square root of 2 gives you this result, and 2 times the square root of 2 gives you the exact same result. So those really are the same value, even though at face value they don't appear to be the same number. So how can that be? Well, notice if I take 4 divided by the square root of 2 and I multiply that by the square root of 2 divided by the square root of 2, then I'll get 4 square roots of 2 in the numerator, and the square root of 2 times the square root of 2 is just 2, and so I can cancel the 2 and the 4 then, and that will give me 2 square roots of 2. So you see they really are the same. But since radical expressions that appear to be different may describe the same value, you see it's going to be necessary to have a common rule of simplification so that one student doesn't get this answer and another student get this answer, and maybe they think they have the wrong answer. All right, so in the days before calculators, when decimal computations were done by hand, it was much easier to multiply 2 times the square root of 2, that's this one right here, the square root of 2 is about 1.414, than it was to divide 4 by the square root of 2, right? This would be a really cumbersome calculation here. This one is much easier, and so the standard rule for simplification in regard to radicals was to always rationalize the denominator. In other words, get rid of this irrational number in the denominator, 4 divided by the square root of 2, and make it a rational number by multiplying as we did right here, and then I get 2 in the denominator, and that's much easier to divide by, or in this case we just cancel it out and became a simple multiplication problem. Okay? Now there's 2 related ways that you can rationalize the denominator by working either inside of the radical or outside the radical. So these first 2 examples illustrate this. If I had the square root of 6 divided by the square root of 7, or the square root of 6/7, notice that these are exactly the same. I could just write this as the square root of 6 over the square root of 7. If I did like I did above, I just multiply by the square root of 7 over the square root of 7, and I would get the square root of 42 over 7. Okay, the square root of 7 times the square root of 7 is just 7. Now, I could also do that within the radical. I could think to myself, I know that when I simplify this radical, I'm going to end up with, the square root of 6 over the square root of 7 like I did here. But if I multiply inside the radical, what could I multiply by so that this denominator would be a perfect square, so that when I take the square root of it, the square root will go away. All right, so I could just multiply inside the radical by 7 over the 7, which is really the same thing as multiplying outside by square root of 7 over square root of 7. And that will give me the square root of 42 in the numerator. And then I get the square root of 49, and the square root of 49 is again just 7. Okay, so either way, you'll of course get the same answer. All right, so for this example, if I have 3 square roots of 5 over 2 square roots of 2, I could just multiply by what I need to make the radical go away. Notice I don't have to multiply by this 2. It's just going to hang out there. Let's just multiply by the square root of 2 over the square root of 2. So that would give me 3 square roots of 10 in the numerator. In the denominator, I'd get 2, this 2, and then the square root of 2 times square root of 2 is just 2, so I get another 2. So my answer here would be 3 square roots of 10 over 4, and I've rationalized the denominator. I've gotten rid of the radical in the denominator, and this would be the simplified form, and that's the rule that we have. We typically do not want to leave radicals in the denominator. All right, so let's move on to 2 more examples here. And the significance of these examples is that the denominator has a factor in it. That's a perfect square. In this case, 12 is equal to 4 times 3. So when I come to simplify this and to get rid of the radical in the denominator, I don't want to multiply by 12 over 12 because then I'd have a 12 in the numerator and I'd have to simplify the square root of that 12. So it's better to go ahead and factor that 12 first. Think of 12 as 4, because 4 is a perfect square, times 3. And then, since I'm already going to be able to bring this square root of 4 out, I can just multiply by 3 over 3. So this will give me the square root of 15x in the numerator, and then I'll have the square root of 4, which is 2, and the square root of 9, which is 3. Okay? So my final answer here would just be the square root of 15x over 6, and that would be the easiest, best way to do that. Same thing here. Let's go ahead and simplify the 32a squared b, or at least factor it, so that we can see that there are some perfect square factors in this. Let's write that as 16 times 2 gives me 32, and a squared is a perfect square as well. And I have the b. So this is the part that's not a perfect square, so I'll go ahead and factor that, and then I'll multiply inside the radical by what I need to make this additional part, this leftover part, be a perfect square. So I'll multiply by 2b over 2b. All right? So notice that gives me in the numerator 14b. So I'll have the square root of 14b, and then the denominator, I'll have the square root of 16. That's just 4. Square root of a squared, that'll be a, assuming that a is a value greater than 0. I'll have 2 squared, the square root of 2 squareds, and 2, and the square root of this b squared will be b. So let's just write this. Final answer is the square root of 14b divided by 8ab. So that would be my answer.